So I wanted to do another homework example for you. This homework is problem 428. And the reason that I picked this along with problem 410 is it shows you the two different techniques that we spoke of how you can compute the moment of a force about a point. And in this case, we're given a force which has a tail at point A. It's expressed in terms of rectangular or Cartesian form. And what we're asked to do is to compute the moment of this force about point P. So remember that the vector formulation of computing a moment uses a cross product as opposed to that scalar formulation. And you may say, well, why don't you just use the scalar formulation here? Well, it would be very hard to get the perpendicular distances for each of the components of this vector. So generally in 3 dimensions, the way that we'll compute a moment of a force about a point. So usually I use a subscript of the actual force that I'm computing the moment associated with. So the moment of this force about point P is going to be nothing more than a position vector from the point of interest, which in this case is P, to anywhere along the line of action of that force. However, if you notice for this particular force, it's going to be very hard to find another point along the line of action other than point A, which is actually at its tail. So I'm going to say that this is going to be the position vector from point P to point A, and I'm going to take the vector product or the cross product with the actual force itself. So the first thing that I actually need to do in order to solve for this problem is to get an expression for that position vector that goes from the point of interest, which is P, to the actual point of application of the force, which is A. So how will I actually do this? Well, I'm going to need the coordinates of both points. So let's see how we would do that. Let's go about writing the coordinates of point A first. So if we look at the geometry that we're given, in order to go to point A along the x-axis, and kind of remember the easiest way to do this is when it's drawn in 3 dimensions, actually projected down on the xy plane. So that's this point here. And you see that the geometry that we're given tells us that we need to move 1 unit in the positive x-axis. So this is the positive direction. So from the origin, we move 1 unit out. And then we move 2 units in the negative y direction. So that's going to be plus 1x minus 2y, and then plus 6z. So the A coordinates are x coordinate is 1, y coordinate is minus 2. That's going to take us down to this point in the xy plane, and then we're going to up 6. So those are the coordinates of A. In a similar fashion, the coordinates of P are, if you notice, it's purely in the yz plane, so there is no displacement in x. We're just going to leave x equals 0, and then we'll move in the y direction 4 units, and we'll move up 3 units in z. So the coordinates of point P are 0x, and then 4y, and then 3z. So in order to write an expression for a position vector that goes from point P, I should say, that's the tail, to point A, and that is the tip, I'm going to take the x coordinate of A and subtract away the x coordinate of P, and that will be the I hat component. I will take the y coordinate of A minus the y coordinate of P, and that'll be the j hat component. And I'll take the z coordinate of A minus the z coordinate of P, and that will be the k hat component. So how do I actually do this? Well, I just need to substitute in. The x coordinate of A was 1. The x coordinate of P is 0. The y coordinate of A is minus 2. The y coordinate of P, that's kind of hard to see there, is 4. So minus 2 minus 4. That is the j hat component. And the z coordinate of A is 6. The z coordinate of P is 3. Just do some arithmetic here, and I get that this is, and I'm going to write it in, well, actually, I'll show one more step. 1 I hat. Here, minus 2 minus 4 is minus 6 j hat. Here, 6 minus 3 is just plus 3 k hat. So you can write that if you want in that compact form that we often show, 1 minus 6, 3. And this will take on the units of the individual coordinates, which just is in meters. So always do a sanity check. Ask yourself to go from point P. Helps to be able to see the geometry to do this. To go from point P to point A, which direction do you move in x? Well, we need to move out of the plane in x, so that's going to be in the positive x direction. So the x component of the position vector from P to A should have a positive x component. It should have a negative y component, because that's the direction that we have to go, and it does. And it should also have a positive z component, because I'm going to have to go additionally up. So out in x, over in y, and up in z. So this, at least the signs of these various components of the position vector make sense. So step 2, I'm going to compute the actual cross product, and remember that that is the cross product of our PA and F. And the way that we showed how to do this by hand is to actually set up a 3 by 3 matrix where the entries in the first row are the unit vectors along the x, y, and z axis. So I hat, j hat, and k hat. So these are our unit vectors. And then in the second row, we're going to put the components of our position vector from the point about which we're computing the moment, P, to any point along the line of action of the force, in this case, at. And that position vector, we determined it to be 1 minus 6, 3. And then in the last row, we're going to put the force that's actually causing the moment in this case. So we were given, if you go back to the original problem description, that the x component of that was minus 6, the y component was 4, and the z component was 8. So if you recall, the way that you actually compute the determinant of this matrix is you do a cofactor expansion along the first row. So beginning with the first row, first element item, or entry, I should say, you'll cover that row, you'll cover the column. Since we're beginning with the first row, first column element, cover the first row, cover the first column, and you're left with a 2x2 matrix down there in the lower left. So you're going to weight that determinant of that 2x2 matrix by I hat. So that 2x2 matrix, which was left, was minus 6, 3, 4, 8. And then we're going to move along the first row and continue our expansion. But recall that when you go from the first element in the first row to the second element, the j hat is going to have a negative sign associated with it. It goes plus, minus, plus. That was just the rule. So what is the 2x2 matrix associated with this element in the first row, second column? We'll cover the second column, and my finger is too fat for that, and cover the first row. And you're basically going to see, you're going to get the matrix 1 minus 6 in terms of the first column, and 3, 8 in terms of the second column. So 1 minus 6, 3, 8. And then in a similar fashion, finish out expanding along that row by taking the element k hat. And when you cover the third column in the first row, you see your 2x2 matrix that you're left with is 1 minus 6, 4. When you have a 2x2 matrix, the way that you take a determinant is you take the product on the downward diagonal minus the product on the upward diagonal. So let's actually just do what that math is. Minus 6 times 8 is going to be minus 48. And then we're going to subtract away the product of the upward diagonal, which is 12. Then we have our minus j term. What is the actual value of this determinant? 1 times 8 is just going to be 8. We're going to subtract away minus 18. Minus 18 is just going to be plus 18. And then we have the plus k hat term. And what is the actual determinant here? 1 times 4 is 4. And then we're going to have minus 6 times minus 6 is plus 36. So that's actually going to be minus 36. So keep track of that. When you take the downward diagonal minus the upward diagonal, minus times minus is plus, so it's going to be minus that value. So let's actually see what this turns out to be. The I hat component should be minus 60. The j hat component, we're going to eventually put that negative in there, is 8 plus 18, so that's going to be 26. And the k hat component for minus 36 is going to be minus 32. So the compact way you would usually write this moment of this force about point P is just as minus 60 is the I hat component, the j hat component is minus 26, and the k hat component is minus 32. What are the units of that? Well, will be the units of the position vector times the units of the force vector. So since the position vector was in meters and the force vector was in kilonewtons, this will be in what is known as kilonewton meters. And what you were asked for in that problem, I believe, was the individual components. So this would be your mx component, this would be your my component, and this would be your mz component. So hopefully that was helpful for you. Really, the actual challenge there is just making sure that you're careful and doing your cross product. But once you've done a few cross products, hopefully these will become relatively easy for you.